Here's a proposition for you. Let's say you can buy an unlimited number of $1 tickets. And on each ticket, you have a 50% chance of winning $1, a 10% chance of winning $2, a 1% chance of winning $20, and a 0.001% chance of winning $1,000. Okay? The question is, if you had $1 million, would you buy 1,000,000 tickets? Would it be wise to spend $1 million on 1,000,000 of these tickets, given a guaranteed payoff according to this scheme? You might stop at this point and decide what you would do. See if you can figure out a way to analyze the problem. Okay, now, our expectation is that we're going to win $1 on 50% of our 1,000,000 bets, since we have a 50% chance of winning $1 on any ticket. Okay, so out of our 1,000,000 tickets, we expect that 50% will pay $1. Well, 50% of 1,000,000 is 500,000, so that's 500,000. That's going to be $500,000, isn't it? Okay, and then we also expect that we will win $2 on 10% of our 1,000,000 tickets. Well, that's $2. 10% of 1,000,000 is 100,000. That's $200,000 there, isn't it? Now we win $20 on 1% of our tickets. 1% of 100,000 is 10,000. $20 on each of those 10,000 tickets will be $200,000. And then we're going to win $1,000 on 0.001% of our 1,000,000 tickets. Now 0.001% is how many? Well, that's 10. 0.001% of 1,000 of 1,000,000 is 10. So that's 10 times $1,000. There's $10,000. Now, do we come out ahead? Well, let's look at our totals here. Okay? Is this a good investment or a bad investment? Well, we get our 500,000, our 200,000, our 200,000, our 10,000. That means that we expect to win $910,000. That's our expectation. Now, we don't really expect that we're going to win exactly $910 because this is all chance, right? There's a 50% chance in each ticket. That doesn't mean we're going to win exactly 500,000 times, right? But it's going to be pretty darn close. And actually, the numbers will always stay pretty close to 910,000. They probably won't deviate by more than $20,000 or $30,000 in one direction or another. This means that we spent $1 million to earn 910,000 expectation, which means that we're making a real bad investment. This is not a good idea. Now, the question comes whether we want to spend $1 on that remote chance of winning 1,000. If we've got $1 to spare, then maybe it'll be fun to scratch the ticket or whatever and see if we win the 1,000. There might be $1 worth of entertainment value in that, $1 worth of frustration. It might be that if we don't get $1,000, something awful is going to happen to us. And we've got $1, we don't have any other way of getting 1,000, so we spend $1 in the remote hope that we'll get that 1,000 so something awful doesn't happen. This is the way lotteries work. This is the way lotteries are set up. Out of 1,000,000 tickets bought, generally lotteries might think of paying back $910,000 and taking the $90,000 as profit. If people make good decisions in lotteries, there's probably no objection to lotteries. The objection comes from people who think that it's really kind of a tax on stupidity, that a lot of people will spend money for stupid reasons, not understanding the probabilities and using money that they really need for something else. So there are arguments in both ways about lotteries. Expected winnings per ticket. Okay? Well, on one ticket we figure we have a 50% chance of winning $1. Well, 50% chance of winning $1 is worth 50 cents. a 20% chance of winning $2 is worth 20% of $2, or that should be 10% of $2, not 20%. Don't have the right marker to change that, but I'll use the big one. Okay, now that's 10%. 10% of $2 is 20 cents. 1% of $20 is 20 cents. And 0.001% of $1,000 is $0.01 or 1 cent. And when we add these up, not sure what I was thinking when I wrote that down, but we get 91, not 93 cents. So that our $1 ticket is worth only 91 cents, which means that our expectation on the average is that if we buy a number of $1 tickets, we lose 9 cents per ticket. So really, it doesn't cost us $1 to play this game. It costs us 9 cents to play this game. And it might well be worth the entertainment value as long as we're not spending our kids' food money or something. Okay. This generalizes into the idea of expectation. What did we do up here? We multiplied our $1 payoff by the probability 50% of the payoff, and added the $2 payoff times its 10% probability, the $20 times the 1%, and so forth. The expectation that, well, the process that we used is summarized here. Okay, we got an event, E1. In this case, E1 might have been winning $1. So we take the probability of E1 times the payoff of E1. The 50% probability times the $1 payoff. E2 might be winning $2. So the 10% probability of winning $2 times the $2 payoff, and so forth. We add up probability times payoff. Okay? We add all these up, and that's our expectation. A slightly more concise formula with a little less meaning, but if you know what the numbers mean, it makes perfect sense, is that expectation is probability of the first times A1, where A1 is the payoff. We can't use P for probability and for payoff, so we use P for probability and A for payoff. So probability of the first event times A of the first event, the payoff. And then probability times payoff for the second event until we run out of events. Okay, just a quick rundown of the idea of odds. Okay, we know that the probability of getting 2 heads on 2 flips, this is implicitly for 2 flips of the coin. You can tell that by what the probability is if you don't have any other way, but I'll state it. The odds of getting 2 heads are what? Well, odds mean we have a 1/4 probability of getting 2 heads and a 3/4 probability of not getting 2 heads. So we say that the odds are 1/4 to 3/4. The odds of getting it to the odds of not getting it. Okay? And 1/4 to 3/4 odds can be expressed as 1 to 3. It's just the ratio of these two numbers that matters, so that there's all kinds of ways to express it. But we usually express it in terms of integers, 1 to 3 odds. The odds against getting 2 heads are 3/4 to 1/4, because there are 3 ways to get it. Or 3/4 probability of not getting it, 1/4 probability of getting it, or 3 to 1. 3 outcomes in favor, 3 outcomes against getting it, 1 outcome in favor. Okay? We generally define odds to be the odds in favor of an event are the number of outcomes for E, that is in favor of E, to the number of outcomes against E. Okay? Now, if we look here at the probability of an event, it's the number of outcomes for E over the total number of outcomes. How does that use these quantities? Well, the number 4 is the total of outcomes for E. The total number of outcomes is the number 4 plus a number against. This number plus this number. So if we know odds, we know the for and the against, we can compute probability fairly easily from this formula. The probability of not having an event is 1 minus the probability of an event. Remember, the odds are the probability of the event to the probability against the event. And the probability against is 1 minus the probability of the event. So we have probability of the event to 1 minus the probability of the event. And we use that up here when we said the odds in favor of 2 heads were 1/4 to 3/4. 1/4 is a probability in favor, 3/4 is a probability against getting 2 heads.